Alright, this is Computer Graphics Video 5. This is on perspective projection. So the idea here is to understand what things look like when we look at them. So for a little intro, let's just look at a simple picture, right? And so what we'll do is we'll draw this picture, we'll play around with it, then we'll look at a two-dimensional mathematical version, and that'll scale up to a three-dimensional mathematical version. But picture that you have an eye right here, and your eye is looking at an object. And maybe the object is something like a cube that's out here in space. And so when you look at that, you see a sense of perspective. And the best way to model that is to imagine that there's like a screen between you and the object. What happens is each point on the object, if you draw a line between your eye and the point, and then see where that line hits the screen, you get a bunch of points. Right? And so what ends up, I won't draw the whole thing right here, but what ends up here is we say this, we project each point from the object let's say towards the eye, let's say, and see where the line hits the screen. This gives us a sense of perspective. So for example, a cube would look like this. You'd see the points that are close would be larger. The points that are further away would be smaller. And if the size distinction isn't quite clear just yet, when we draw a two-dimensional version, which will help us work out the mathematics, we'll see what's going on. So here's sort of a two-dimensional idea. And so this is the way we'll set it up. We'll take the XY plane. And we'll imagine that your eye is up here at some D. And then what we'll do is we'll imagine there's an object down below the x-axis. And so we won't work with the entire object, but imagine there's a thing down here. And so what we'll do is we'll pick a particular point on that object. So say this is the point of interest. So look at this point. And what we'll do is we'll project that to the x-axis. So the x-axis will be like our screen right here. So we'll say project to here. So then we can see, for example, that when we do that, that point ends up right there. So that's the result of the projection. And so we can see very easily that points that are further away are sort of closer together. So if we were to imagine, say, for example, here's your eye up here. Imagine a cube down below the x-axis. And let's just project just the four corners of the cube. So if we project this corner, it goes right here. If we project this corner, it goes right here. But the corners that are further away, those look smaller to us, to the eye. So we can say further becomes smaller from that sense of perspective. So this is where the perspective comes from. So what we'd like to do is model this mathematically. So what I'll do is I'll do the two-dimensional idea. We'll work out where the point would need to go. In other words, we'll take a specific point and see how it would need to project. Then we can say, like, okay, by analogy, this is what it would look like in 3D. And then we can see how this works with the matrix arithmetic that we're doing. So let's do some 2D math. So this is actually ridiculously simple math. So we'll have the XY plane. We'll have our D up here. We'll have our point XY down here. What we need to do is we need to say, where does it end up? Right. Well, this is of course the point, some other x, let's say x prime, comma 0, because there's no y value. And so what we'll do is we'll just look at the two similar triangles in the picture. So there's this triangle, the blue one. Then there's a larger triangle, which we'll do in green, which is right there. So if we look at the lengths of these things, right? So this length is x prime. This length is x. This height is d. And this height, so the y value is negative. So this is actually d minus y. Or if you like, it's the difference between, it's d minus a y, which is negative, and that makes sort of a bigger result. And so by similar triangles, right, we have x prime is to x. And the variety of ways you could do this, we'll say x prime is to x as d is to d minus y. So if we solve for x, we get dx over d minus y, or this can be simplified a bit or rewritten a bit. Simplified is arguable, like this. So if we were doing a two-dimensional version of perspective projection, this is what we would need. We would need the point xy to go to the point x over 1 minus y over d, comma 0. Now, if we were doing this representing our points with the extra 1 that came up earlier. So if we're representing xy by something like xy1, because this is what we've been doing, then this is what we need. We need the point xy1. That would need to go to the new point x over 1 minus y over d, 0, 1. So that's what would need to happen in this picture to the left, representing points with the extra 1 in this third coordinate. So likewise, what happens in 3 dimensions? So 3. So in the book, I go through this all in detail, but here I'm just going to sort of use the analogy. But the analogy would be the following. If we repeat this in 3D, this is what we get. So in 3D, our points are x, y, z, 1. And what happens is this would need to get mapped to, and what I'll do is after I write this, I'll draw the picture just so we see what's sort of visually happening here. This would need to map to x over 1 minus z over d, y over 1 minus z over d, 0 and 1. And what's happening in this picture is the xy plane is the thing we're projecting to. The eye is up here, and the point that we're projecting is down below the xy plane. So what this is doing is this is projecting this point to here. This is so the object basically in this picture is down below the xy plane. And so we project this point, this is from, and this is to, right here. And this mapping that we've just drawn, this is the one that would need to do it. Well, this is the function, if you prefer the word function. So this is the three-dimensional version of what's happening in two dimensions on the left. The difference, of course, being that the z replaces the y, and then we have both an x and a y instead of just an x. So then, of course, there's this looming question is, can we represent this with matrix multiplication? So let me clear the screen and then pose that question, and then answer that question, and then fix up a problem that's going to arise. So can this, again, let me just remind you, can this mapping be represented by matrix multiplication? In other words, can you find a matrix M so that you multiply it by, let's just clarify, like by this and get this? The answer, unfortunately, is no. Right? This turns out this is not a linear map, doesn't work. So what do we do? So what's interesting is this one that's been sitting in the fourth position, which was only useful for translation so far. This is going to sort of kick in and be useful again. So take a look at the following. So observe the following matrix multiplication. It's not entirely clear where this comes from. That's okay. We're not going to derive it. This is more of an observation that it does the work. So if we take this product, we multiply it by xyz1. What happens if we do this is we get x, y, 0, 1 minus z over d. Now, if you compare these two vectors, you might notice something really kind of interesting. You might notice those are the same, except well, they're not the same, but to get between them, I need to take the second one and divide by 1 minus z over d. Right? So right here, if we divide this one by 1 minus, let me clarify that correctly, by 1 minus z over d, we get this one, the desired one. So what's the practical upshot of this? Is that we can kind of do perspective projection using matrix multiplication, right? So this is what we do. We define P of D. So P of D is going to be a matrix. It's going to be that matrix in the lower left. Then to project this is what we do. So to project, we multiply P of D by our point, the z coordinate that results, or the fourth coordinates, which result will probably, almost certainly, not be 1. So we then divide by it. Let's say divide the entire vector. By that fourth coordinate. To get the result. So it's not perfectly linear, but it does the job. So let me clear the screen and show you just on a very specific point. So for example, let's project the point -3, -3, -3 with d equals, say, 10. So just so we're clear what we're doing, we don't need a picture for this, but it'll help us understand what we're actually processing, is we're putting an I up at z equals 10. We're taking a point which is at -3, -3, -3 back here, and we're projecting it to the xy plane. So here, so maybe more concretely, we're projecting -3, -3, -3 to the xy plane via a line to 0, 0, 10. That's our d equals 10. So what we do is the following. So this is really, really simple. So we simply do p of 10 times our vector -3, -3, -3, 1. When we do this, our p of 10 is that matrix from the previous page. We multiply it by this. When we do that, we get -3, -3, 0, 1.3. And then we fix the damage, right? Because if you look at this final point, at this final coordinate, this is not 1 anymore. So what we do is we divide that vector by 1.3. So when we do that, what we get is -2.308, -2.308, 0, 1. And then we extract the point. The result is -2.308, -2.308, 0. That's the result of the projection. Now, the one thing we need to be careful about is if we do multiple points at once, we have to fix them all sort of simultaneously. We have to fix them all independently from one another. Right? So consider now. Well, let me do that on the next page, but I'll say note. If we do several points at once, we need to fix them independently. Let's look at an example where we can draw like an entire picture and see something meaningful. Right? So consider the following cube. We'll do a cube with corners. So all these corners are below the xy plane. So the first one is the value we just did. And then we're going to mix and match the threes a little bit. This is a 6 by 6 cube. So if you were to draw this, we don't need to draw a perfect picture, but those 8 points rather would be down here. And what I'll do is I'll draw some lines between them. The lines are not really part of the picture, but they help us get a sense of why there's actually a cube here. And the top of the cube is at -3, the bottom of the cube is at -9, and then it's plus and minus 3s all the way around. And what we're doing is we're going to project that to d equals 10. Or let's say project with d equals 10. So what we're basically doing is the entire calculation we just did, but we can, interestingly enough, do this all at once. So what we'll do is we'll take all of these points and we'll put them together in a vector. So we'll, let's say, project with d equals 10. So for a solution, this is what we do. Is we construct a matrix which holds all of these points in one fell swoop. So let me pause the screen and fill these in. This is the matrix we construct. This is a matrix, if you like, of points. Then what we do is we project them all at once. So we take P10 and we multiply it by A. So the reason is when we multiply P of 10 times A, that effectively multiplies P of 10 by every single coordinate independently. Or every single column, if you like, independently. So if we do this, this is the result. Again, let me fill this in quickly. So this is the result we get when we do this multiplication. And then what we have to do is we need to sort of fix each column. This has to be independently by dividing each column independently by its fourth entry. So when we do this, this is the result. That's the result right there, quickly filled in. So if we take those and if we plot just the first entries, or really just the first two, because now we're looking at the XY plane, we can see immediately what this will look like. Because if you look at the first four entries form a square, the second four entries form a square, the second four entries square is smaller. So what we're seeing is this. And so what's happening is the top of the cube, again, these lines aren't really in the picture, they're just helping us see. The top of the cube is bigger because it's closer. The bottom of the cube is smaller because it's further away. And that's the result. And that's what happens when you look at this cube right here projected onto this screen using this projection. Right? This thingy right here is a result that shows up. If we go back to that original picture, it shows up right in there. Is this picture that we just drew right here. So what's really great is now we have all these tools, we can combine them all to get rotations and translations and so on and so forth. So let me just end with like a big combination problem where we mix and match a bunch of the things that we've done. So I won't write out every single detail here because the matrices are long and arduous and these are all in the textbook. And you don't need to see me, you don't need to sit here watching me write all these numbers down. But here's the basic idea, right? So let's take the same cube as above, as before, with all the plus and minus 3's. What we'll do is we'll first rotate it about the x-axis by pi over 6, then the y-axis by pi over 12, then shift in the z direction by -1, then project with d equals 10. So this is all really, really nice and easy, right? So we have a matrix for each of these things. So what we do is we multiply each of these matrices. Ooh, I realize I forgot a rotation. If I'm copying the book, I want to make sure I have this. So then the z-axis by pi over 12, and the y was supposed to be a pi over 3. Sorry, I got a little confused there. So what we do is we have 5 matrices we need to apply, right? So we take our A. A was a collection of points from before, right? The plus and minus 3's and the 9's and so on. Right? We take that thing. The first thing we do is we rotate it around the x-axis. So to do that, we do Rx pi over 6. That goes first. Then we multiply around the y-axis by pi over 3. Then the z-axis by pi over 12. Then we shift it in the z direction by -1. And then we project with 10, right? So again, this is all the things going on. This is the rotation around the x. This is the rotation around the y. This is the rotation around the z. This right here, this is the translation. This is the projection. We can multiply all of these as just a giant big matrix multiplication. If we do this, this is what we get. So I won't write the entire thing here, because it would just drive us crazy, and these points are all fairly icky. But I'll write a few of them. I'll write the first 2 columns. Again, these are all in the textbook. These go on and on and on. There are 8 columns because 8 corners. And then we scale independently. So we scale each column. So the result of doing that, again, I'll just write the first 2 columns just to save us some sanity. But we're scaling them so the 4th entry is 1. And if we extract for each of those, if we extract the first 2 entries, this is what we get. This is in the XY plane. Let me draw these slowly. I won't try and make these perfect, but good enough. And then I want to draw the connecting things between these. So it turns out that one side of the cube turns out right here. Again, I'm filling in these lines just to sort of help give us a sense of perspective. Second side of the cube. Right there. Right there. So that's what happens. That's what all those rotations and translations do to the cube. That's a perfect example of how we can sort of mix and match all of these different pieces together to get us like a full set of actions and a good perspective projection at the end. So let me stop right there. That's the end of that video. Mostly the end of the set of videos for this. I may do one more video that contains a few examples, but if this one makes sense, then they'll all make sense.